In this part, we are continuing with diffraction, where we are studying the diffraction of light of a monochromatic light and through a single slit. And we had already discussed about the case of diffraction through a single slit, where the central maximum was formed when the parallel light rays moving parallel to the direction of the distance between the slit and the screen, having no phase difference between them, result in a constructive interference giving a central maximum. And again, we also mentioned that if there is some path difference, which is shown in the figure in front of you, where we have constructed the light rays which are moving slantingly. So the wave fronts over there, the wave front is obviously in that slanting dashed line. The first dashed line that you see between the slits, again a highly magnified view of the distance between the slits, which is d. And then what I had also mentioned is that for the phase difference or the path difference, first of all we consider uh, the point by dropping a perpendicular from the topmost point. Let's say this is the point A at the top, and there's a point B at the bottom, for the width of the slit being AB, which is equal to D, and BT over here is the path difference between the first and the last segment, or the last portion, or the last ray, which is emanated from the given slit. Relation between this slit width and the path difference that we had mentioned is equal to well, that x is equal to simply d sine theta, where theta is obviously the angle through which the rays are slanting. Now you can refer to the diagram that we had made in the previous video, and from that diagram we have uh, these geometrical terms, or geometrical um, um, parameters that we are using in this video. Now, as these light rays are slanting, we divide this into two segments. Now here is, as you can see, the first segment, and this is the second segment. Now between the first and the second segment, with this path difference being at the end between the first ray and the last ray that we have considered, if that path difference is equal to some value which is equal to lambda. Actually, the lambda is the wavelength in this case of the light that has been projected through that slit, and with the value of x being equal to lambda, what we get is, from a basic proportionality, or you can say the midpoint theorem as well, this length over here will be lambda over 2. And because this length is lambda, so that halfway through that length will be lambda over 2, because we have constructed that line in halfway, where we can say that this is the point. Let us say this is some other point, we name it as M. So AM is actually equal to MB, and that is equal to D over 2. And similarly, if we name this point, let us say as N, we have AN to be equal to NT, and that is half of the entire value. Well, that will be simply equal to d cosine of theta. We need not be concerned about d cosine of theta. However, we can just mention it for just the sake of mentioning. So now these assumptions, or rather this geometry, which is not an assumption, of course, this is completely valid. So we have, for this being lambda, we have this as lambda over 2, and what that does is that when we have the path difference as lambda over 2, we have the phase difference as 2 pi over lambda times of x, which is equal to 2 pi over lambda times of lambda over 2, which is x, the value of x that we have used. So the lambdas get cancelled out, the 2's get cancelled out, and what we are left with is pi. Pi is the phase difference, meaning that they will interfere destructively, one wave over the other wave, destructive interference, and that would result in a minimum. So each point between this wavefront starting from A through to N, each point will interfere destructively between the points through from N through to N through to T. So AN, all the points between AN, they are going to interfere destructively. Those wavelets that will generate those wavefronts, they are going to interfere destructively with all the points below in that segment 2. So segment 1 interferes destructively with all the points in segment 2. And as a result of this, we have the condition of minimum, or the minima that we get obtain on the screen. Now, obviously, that was focused at the point y. So, under what conditions do we get minima at the point y? Well, the condition is simply, if we are to generalize this thing, we will have x to be equal to some n times of lambda, and or we can say that it is 2n times of lambda over 2. Now remember, this value x is equal to even multiple of lambda over 2 was obtained for the maxima in case of interference. However, this is the condition of minima in case of diffraction, completely opposite. And again, there's one more exception that we must consider, is that we cannot choose n to be equal to 0 over here. N is equal to 1. N is equal to 1 is equal to 2, and it goes on. Why n is not equal to 0 is what we will be discussing later, a bit later in this video, so hang on to that. But uh, that's the exceptions that we have to consider in this case. Now let's consider the cases where we obtain the maxima, or the maximum intensity, and in this case, as I had already mentioned, the maxima obtained other than the central maximum will be lesser, will be of lesser intensity, and will gradually fade away as we move away from that central maxima on either side, and therefore they are called as secondary maximum or secondary maxima. So let's just look at the conditions that lead to the formation of secondary maxima. So we'll consider that diagram once again, only this time we'll have 3 segments instead of 2 to consider. We can consider any number of segments because that single slit can be divided into any number of segments as per our requirement. So we are because this is what uh, we are independent of doing, because uh, that's a free space available for us. So that's a single slit, of course, but then again, the space that is available, that can be considered to be multiple slits over there, small slits. So we have chosen 3 segments out of it. So in that case, with the given conditions, those 3 equal segments, of course. So here A to M is D over 3, then M to O is D over 3, and O to B is simply D over 3. So equal parts. And as a result of that, when we choose this value of x, which is the path difference in this case, of course, and that value is, let us say, an odd multiple of the half integral of lambda, that would result in this portion, that is OP, that would become equal to, let me write it over here, that becomes equal to lambda, which is 2/3 of 3 over 2 lambda. And then this is 1/3 of that, and 1/3 of that means 1 over 3 lambda over 2. So this is simply lambda over 2. And as we know that for the path difference being lambda over 2, the segments 1 and 2 considered, they will interfere destructively. But however, with their destructive interference, that would hardly impact the third segment, which will interfere constructively, because there is nothing to destroy it, as we can put it. So this is going to be a constructive interference. But as you observe, as you might have observed already, that two of its segments have interfere destructively, while only one segment, that is the third segment, is available for constructive interference, and that would result in only a one-third intensity for the maximum. And that is why the maximum that we obtain is a secondary maximum with lesser intensity, and almost one third, as you can see over here, rather than the case with constructive interference leading to a maximum intensity for the central maximum. So the central maximum has the maximum intensity. Thereafter, if we are to generalize this thing, we would consider an odd multiple of lambda over 2 as the path difference that would lead to the formation of the secondary maxima. Now remember, again, I must bring to your notice that this was the condition of minima in case of the interference of light, and also the case that we considered for Young's double slit experiment. So and now we have the just the opposite conditions, and again for this case as well, we cannot take n to be equal to 1, which is what I'm going to discuss right away. Now, given the geometry of the slit that we have considered, uh, in that case, as I mentioned earlier in the previous video, that this again is a very, very large length when compared to the length that we consider, uh, when compared to the lengths we consider between the slits, as well as the uh, perpendicular distance between them. Now, this is supposedly the case with two slits over here, and one of those rays is moving in that direction, and the other ray is moving in that direction. The difference over here is the path difference that we are going to get. That is x, as we have already constructed this. But uh, let's just consider this, because they are very. This is very small in comparison to this length d. So what we do is we can take this as the angle theta, because if this line is moving at an angle theta, so is the line below it. The angle theta hardly is anything different for the two lines with that kind of length or dimension considered. So if this is theta, then what we also obtain is tangent of theta. The Obviously it is very small again, and because of that, the tangent of theta is equal to, in this case, as you can see, is y over d, not small d but the capital one, and that is simply equal to sine theta, because theta is very small. And as a result of that, what we get is, for the value that we have over here, that is x is equal to d times of sine theta, we have x is equal to d times of, instead of sine theta, we can just put the value y over d, and then with this equation we have y is equal to x times of d over d. Now this is quite familiar, that the case that we obtained in the Young's double slit experiment, and even in Young's double slit experiment you can consider this kind of a setup to derive to come to this equation rather than the one that I had used of S2P minus S1P and all of that. So this is fairly easier if it looks easier to you. Uh, the in order to put that on your paper, exam paper, you can use this kind of derivation, or you can stick to the basic derivation of taking the Pythagoras theorem into account and then using to obtain the difference, the path difference, that is S2P minus S1P. You can refer to the derivation that I did in Young's double slit. So I have already given you two derivations for the same thing. You can use whichever you feel is easier. Now, y is equal to x d over d, because we have the conditions for x over here, so we also have y to be equal to an even multiple of lambda over 2 d over d. This is the condition. These are the positions for the maxima. And again, with y available for this as well, y is equal to 2n plus 1, which is the odd multiple of lambda over 2 d over d. That is, or those are the positions where you will be obtaining the secondary maxima. I beg your pardon, I said maxima over here, it's actually minima. And the secondary maxima for all those values of n other than 0. You know why we cannot use 0? Because 0 is already booked for the central maxima. But one would argue that, well, it's for central maxima, so what's the problem with this? Because the secondary maxima is obviously not going to coincide for n is equal to 0 at that point. Because if we put n is equal to 0 over here, then we are going to get y to be equal to lambda d over 2d, which is obviously not 0. So what's the problem with that? Well, the problem is that it's coming within the width of the central maxima. You see, if we have now you can consider looking at the top of your screens. If we have that maximum over there, and the secondary maximum is obviously going to follow after that minimum. So these are the minimum points, which are obviously not completely 0, and the secondary maxima are going to follow after that. They cannot lie within that range. So what's important for us is to determine the value of these two secondary maxima, these two minima, so that we can calculate the width of the central maxima. Now from this over here, if we put n is equal to 1 and minus 1, then we can determine the value of these two minima, and then the difference between them is going to give us the width of the secondary maximum. Now obviously as you can observe very closely, that if we put n is equal to 1 and n is equal to minus 1 for these two, this one n is equal to minus 1 and this one is equal to n is equal to 1, and we use this formula over here, then we get the width of the central maxima as simply being equal to well, that is equal to 2 times of lambda d over d. You can subtract and check for yourself. So that's the width of the central maxima, and that's obviously this value over here that we considered, that cannot lie within that central maxima, this one that I've obtained. This thing, where's that gone? Yeah, this one. This one cannot. If you can excuse me for a second, I have to plug in my laptop. It's not, the battery isn't really good. Okay, so we are done. We are back to normal. So this one cannot lie within that range, and that is why we cannot use the value 0 over there as well. We have to start from n is equal to 1, 2, and it goes on, and so is the case with this. So with these things, we have completed the condition or the diffraction through a single slit. I'll be giving you further details about a few more things which are obviously not a part of your course, but definitely they were a part of the earlier course, and they were uh, pretty much valuable to know. So I'll be giving that, but that will be the extra bits that I'll be giving out. As of now, this is the portion that was required for that CBSE course of Standard 12 physics in the case of optics, and we have completed that as of now. More details, a little bit of extra points will be given out in the next few videos. Till then, thank you for watching.